Hi all, in this video let us do example number 2 of ice table problems. Let's see if this one is a bit more interesting. We have a reaction that has this equilibrium constant. What will the concentrations? Question mark. What will the concentrations be for all three molecules when we start with this much H2, this much I2, and no product. In the previous video, we said we got to figure out first which direction the reaction will go in. Will it go in the forward direction or backwards direction? Well, because we have no product, we are going in the forward direction because we have to make product. So initially, before we reach equilibrium, the reaction goes either to the right or forward or to the products. I'll say goes to products, which means we're making products until we get up to equilibrium. Now, we could also do this using QC. You know that QC in this case equals the concentration of HI, don't forget the squared, divided by concentration of H2 times the concentration of I2. But HI is 0 at the start. So we have 0, and then here we have 0.240, and it's actually squared because initially they have the same amount of H2 and I2. What this tells me is that our conclusion is QC is, it's less than KC, so it's too small. And if the QC is too small, the equilibrium will shift to make more products to get the to get the reaction quotient equal to the equilibrium constant. So this verifies that we are shifting to the right. Same thing as saying you're shifting to the products. This is important because when we set up the ice table, we have to know where the plus x goes and where the minus x goes. The trick is, I like to write out my equation with the coefficients. So just write the equation again. I'm leaving out the phases. They're all gases. And set up the ice table. Like I said in the previous video, you should be using molarities or the partial pressure of a gas. I didn't mention that, and it wasn't important in the previous problem, but the partial pressures of the gas should be in atmospheres. I think we have an example where we're using partial pressures, but not here. We're using molarity, 0.240. I'll put 1 m there, and I'll leave the m off the rest of these values. Start out with no HI, no, what is that? Hydroiodic acid. See, this is important because it's shifting to the right. We are consuming the reactants to make the products. We don't know how much reactants we consume, so we give it an X. Because the coefficients are the same, these two are the same. What I like to do is find the compound that has an implied coefficient of 1 and make the change either minus x or plus x, depending on whether you've determined that we're going to lose some of the molecules or we're going to gain some of the molecules. So this 1 actually is implied right here. 1 minus 1x. This is the trick because I gotta use this coefficient because now, if you think about it, every time we lose 1 molar, how should I say this? Every time we lose 1 molar of H2, we gain 2 molars of HI. We gain 2 molars of HI. Okay. Alright, so hopefully you understand why I like to put the coefficients. There's some techniques where when they write the ICE table, they don't put the coefficients, but I like to because to remind me the ratio of things being lost and things being gained. Alright, we just have to fill in the equilibrium row. 0.240 minus x, 0.240 minus x, and this is just 2x. Okay, those are my equilibrium concentrations, but I just still don't know what x is. Number 3, the third step is to set up your equilibrium expression. So the equilibrium expression is Kc products over reactants, but remember to use the coefficient as the exponent. And then we have concentration of H2, concentration of I2. Some students want to go ahead and jump and plug in numbers, but I feel that's a good way to forget about the exponent, or to kind of reverse the compounds, what goes in the numerator and what goes in the denominator. I'd rather visually see it. Okay, and now we could plug in because I understand now this is parentheses 2x and it's squared. Okay, so yeah, the coefficient here tells us that we have twice as much product being gained as reactant being lost, but in the expression it also tells us we got to multiply, we have to square that concentration. Next we have H2 concentration, which is 0.240 minus x, and you should realize that these two are identical. This is going to help us out because we're going to call this also squared, equals. The equilibrium constant was given as 54.3, and that goes here. Okay, so this is a little more complicated to solve for x than the previous example, example 1, but there's a shortcut and it helps us out so much because instead of expanding this expression, right, instead of saying that this is 4x squared and then this is, I don't know, what is this, x squared minus blah 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 blah, instead realize that you could take the square root of all of these individually. So in green, I'll do it in green. You take the square root, and you're allowed to do that in algebra. The expression will still stay true. You are square rooting, is that a word? Every term. Okay. So what we have here is, let me do this one first, equals square root of 54.3, 7.3689. You don't want to round until the very end. And then all of this, okay, so now we have 2x over 0.240 minus x. Okay, so we still have some work to do. It's definitely more complicated than our example 1. Let us cross multiply. See, I have that number saved already. Times 0.240. So that would be up here, right? 1.7685, and then multiply by minus x, minus 7.3689x equals 2x. Let us bring this term with x to the left. Oh, no, I don't have it saved. So 7 point, so we're going to add 7.3689 to both sides. Plus 2. I hope this is right. Oh no, I have the answer written down somewhere. Okay, that looks good. Equals 1.7685, and then finally 1.7685 divided by that answer. X equals 0.189. Our ICE table was using molarity, so this is molarity. But this number is the concentration of none of these compounds, H2, I2, or HI. We just have to plug in now X. Therefore, the concentration of, let's do the product first, HI equals, that number doubled, times 2. I got 0.3, we'll go with 3 significant figures, 378 molarity. Okay, so we're keeping an eye on this. H2 concentration actually equals also the I2 concentration, and we are taking 0.240 minus 0.189, 0.51 equals 0.051 molar. Let me make sure I have the right numbers. Okay, circle those. It tells us that we have more product, and you see that we're squaring it also in the expression, and our number is indeed greater than 1. It's 54.3, and I think this is good. So here, we should just understand that these are equilibrium concentrations now. Equilibrium concentrations. And what was the trick? Recognizing that we can take the square root of every term in the expression and solve for x. Now, do you realize that if this wasn't 0.24, if these two numbers were different, we wouldn't be able to do this trick because it wouldn't be squared. It would be this times a different number, a different expression. And then we would be most likely doing longhand and expanding every expression and then trying to figure out how to solve for x. Okay, that was a slightly more sophisticated problem than we saw in example 1. Example 3 is going to be, I would say, of equal difficulty as this one. Okay, so I'll see you in the video for example 3.